Welcome to this explainer. Today, we're looking at one of the most breathtaking visual spectacles our solar system has to offer, the solar eclipse. We're going to break down the exact celestial mechanics that make these phenomenal events possible. Because, it's not just giant rocks floating randomly out in space, it is a beautifully intricate, perfectly timed clockwork. And we are going to unpack exactly how it all functions. Okay, let's dive into our roadmap for today. First up, a perfect cosmic coincidence. 2. Anatomy of a shadow. 3. Why not every month? 4. The total solar eclipse. And finally, 5. Annular, hybrid, and partial. All right, section 1, a perfect cosmic coincidence. To really wrap our heads around solar eclipses, we've got to start by just marveling at the sheer mathematical perfection that makes our view of them possible. Think about this logical puzzle for a second. We know the sun is an absolutely massive star, right? And our moon is, by comparison, just a tiny little rock orbiting our planet. So how in the world is it physically possible for that tiny moon to slide in between Earth and the sun and completely block out the face of a giant star from our point of view? Well, the answer is literally a stunning cosmic coincidence. Yes, the sun is roughly 400 times bigger than the moon. That's huge. But, and here's the kicker, the sun is also about 400 times farther away from us than the moon is. Because of that exact, incredibly precise ratio of distance to size, the sun and the moon appear to be practically the exact same size in our daytime sky. Without that perfect proportional setup, the mind-blowing solar eclipses we experience simply wouldn't exist. Moving right along to section 2, anatomy of a shadow. So when the moon casts its shadow down onto Earth, it's actually not just one big solid dark spot. It behaves according to some very specific mechanical rules. The first absolutely crucial term we need to anchor here is the umbra. The umbra is the darker, inner, cone-shaped part of the shadow. If you happen to be standing exactly within this super concentrated area on Earth, the sun's light is 100% blocked by the moon. This is the sweet spot. This is where you get the true magic of total darkness right in the middle of the day. Now, zooming out to build our complete picture, we have the second zone, the penumbra. This is the lighter outer concentric cone of the shadow. Because it wraps around the umbra, it spreads out and covers a vastly larger chunk of the Earth. If you're standing in the penumbra, you're only getting a completely different partial eclipse experience because the sun's light is only partially blocked. And of course, if you're entirely outside both the umbra and penumbra, well, you won't see an eclipse at all. Which brings us to section 3. Why not every month? Okay, it is time to address the elephant in the room. We know solar eclipses only happen during a new moon, which is when the moon and sun are lined up on the same side of Earth. But we get a new moon roughly once a month, right? So logically, why in the world are solar eclipses such incredibly rare events? Well, the crucial point here is the number 5. The moon doesn't orbit in a perfectly flat circle on the exact same plane as the Earth and sun, what astronomers call the ecliptic plane. Instead, the moon's orbit around our planet is slightly tilted. It's inclined by about 5 degrees. And that little 5-degree tilt? It completely solves our mystery. Because of that incline, during almost every new moon, the moon actually sneaks just above or just below the sun from our perspective down here. So those umbra and penumbra shadows we just talked about, they get cast out into totally empty space, completely missing Earth. A perfect alignment only happens roughly twice a year during these narrow windows called eclipse seasons, which is when the new moon precisely crosses that shared Earth-Sun plane. Next up, section 4, the total solar eclipse. When that perfect alignment actually hits during an eclipse season, we get the absolute most awe-inspiring variation of them all. But to experience a total solar eclipse, the universe demands some pretty strict conditions. The moon has to move directly in front of the sun, barely covering its face. And you, the lucky observer, have to be perfectly positioned standing right inside that super narrow inner shadow, the umbra. Because the umbra physically shrinks as it stretches toward Earth, the actual area that experiences totality is incredibly small. We're talking a path often less than 50 miles wide. But man, if you're inside that narrow path, the dark disk of the moon reveals the corona, the sun's ghostly white outer atmosphere that's normally way too dim to see. And since Earth is spinning and the moon is moving rapidly, this whole total phase, it might only last a few brief minutes. Let's round it out with section 5, annular, hybrid, and partial. So, not every perfect alignment actually results in a total eclipse. We're going to categorize what happens when orbital distances and alignments shift slightly. What's really fascinating here is how the non-circular shapes of these orbits alter what we see. The moon's orbit around Earth isn't a perfect circle, it's an ellipse, meaning its distance from us is constantly changing. We use the term apogee to refer to the specific point when the moon is farthest from Earth. And because it's further away from us at apogee, the moon actually appears a little bit smaller than normal in our sky. Now, if an eclipse kicks off while the moon is hanging out at or near this apogee, its shadow plays by different rules. Since the moon is farther out, that dark Umbra cone literally runs out of room. It doesn't even reach Earth's surface. Instead, the shadow that keeps going past the end of the umbra, a zone called the Antumbra, is what hits us. And because the moon appears smaller, it can't completely cover the sun. So observers standing in the Antumbra see this brilliant blazing ring of sunlight, or an annulus, completely surrounding the dark moon. This is what's known as an annular solar eclipse. All right, to really lock in your understanding of the mechanics we've covered today, let's put these four distinct eclipse types side by side. First, the total eclipse. You're squarely inside the umbra. The sun is totally blocked, and boom, you can see the corona. Next, the annular eclipse. You're inside the antumbra, and you get that awesome visible ring of sunlight. Then there's the hybrid eclipse. This one is totally wild because Earth's actual curvature comes into play. The umbra reaches Earth in some spots, creating a total eclipse, but as the planet's surface curves away, the umbra falls short, transitioning the event into an annular eclipse. Finally, the partial eclipse. You're just hanging out in the lighter penumbra, and only a chunk of the sun is covered. It honestly is just incredible to wrap your mind around the sheer vast scale and the precise clockwork ticking away right above our heads. So, I want to leave you with this final thought-provoking question. The next time you look up at the moon on a clear night, are you going to see just a rock floating in the dark? Or will you see the precise, intricate mechanics of the cosmos, silently orbiting and waiting for the absolute perfect moment to align? Thank you so much for learning with me on this explainer, and remember to keep your focus sharp and your curiosity sparked.